Okay, guys, we made it. It's the last section in Chapter 4, which is all about probability. In this final section, we are actually combining probability and the counting techniques that we've learned so far, namely the permutations and the combinations. So hopefully you remember that stuff from section 4.4. If not, go back and take a look at those videos. So one of the big things to keep an eye out here when we do these sorts of problems is looking for keywords, okay, and try to discern some of those things. So let's take a look and see what we've got. So example 1 says a group of 12 tourists visiting London. At one particular museum, a discount admission is given to groups of at least 10. Okay, so that's an important set of phrases there. Now, letter A says how many combinations of tourists can be made for the museum visit so that the group receives this discount. Okay, so first thing we got to make an observation is we've actually got 12 tourists, right? So what this tells me is we get a discount when we have at least 10. Okay, so that means we can have a group of 10, we can have a group of 11, or 12. I hope you agree with that, right? These are the group numbers for this particular group of people that would allow them to get the discount. So it's got to be 10 or 11 or 12. Now I want you to listen to what I just said. I said 10 or 11 or 12. So let me erase this and let me write that. Oops. It should be 10 or 11 or 12. The key word there is or. Now if you remember back in probability, what happened when we had the word or? Do you remember we added? Okay. Now I know this question is not asking for probability, but what it's asking for is how many combinations we have, right? And since we've got three different possibilities, and sort of three different categories you can think of it, a group of a 10, a group of 11, or a group of 12, we're going to add them. Now we're dealing with combinations here. Okay, so what that says is we're going to have three different combinations. Each one of them we're going to have 12 people to pick from, right? Because that's how many are in the total in the group. Now, in order to get the discount, okay, the discount has to be 10, 11, or 12. And so I put those in another color to signal to you the discount. And you notice here that we're adding, okay? So simplifying each of these, I'll let you put them into the formula. Okay, we'll spare you the details on that. We're going to get 66. Actually, I think I got... 66 plus 12 plus 1 equals 79. So there are 79 different groups that we can make out of these 12 that will allow us to get that discount. Now what letter B is asking is suppose that the group of the tourists does get the discount, and we want to know what's the probability that it was made up of a group of 11 tourists, okay? And so what this is really asking for is what's the probability that the group that's chosen is the group of 11, okay, given that they got a discount, okay, that they got a discount. Well, how many groups get the discount? How many combinations of the groups? We know that's 79 from letter A. And what we need to know then is how many in a group of 11. Okay, well, we kind of answered that question. I kept things lined up for us. That should just be 12. Oops, let me write it in the other color here. Keep consistency. There we go. So it should be 12, okay, which is about, I think it's a decimal 0.1519. Okay, so not so bad. At least I hope not. And so you can see here, again, we're combining combinations with a little bit of knowledge on probability and using the word or there to add. Okay, example 2. We have Jack who is setting a password on his computer, and he's told that the password has to contain at least 3, but no more than 5 characters, and he can use either numbers or letters. Okay, so we have a password that has to be at least 3 but no more than 5 characters. Okay, so that means we can have 3 characters or 4 or 5. So this is going to follow very similar to what we did in the last example with adding. Okay, now the question is, can we use permutation or combination here? Does the order matter? Now you have to think about a password, guys. In a password, does it matter the order in which you have things arranged, your letters and your numbers? The answer is yes, okay? And so what that tells me is that order matters here. And I suppose I didn't talk about that in the other one when we were dealing with the tourists. And so actually they told us, right? They told us explicitly combinations. I was gonna say, I don't remember talking about that before. We didn't have to. It was very easy. In this case, with passwords, we have to think about that. So order is going to matter in a password, right? If your password is 123, you don't want a combination of that, right? Because that makes it easier for hackers and that kind of thing to get in. So you want to keep it distinct. It has to be in that specific order. Okay, so since we know that, then that means we're using permutations, and we know that we're adding in between the permutations. Okay, and I know we have cases, right, for 3, 4, or 5. Now the question is, how many objects are we picking from? Okay, to understand that, we know that we've got 26 letters and 10 digits, right? And a character is defined as being a letter or number. That's what it says here, okay? That means we've got 36 total to pick from. So each of these is going to be 36. Okay? And so what we have to do then is figure out what are the numbers. Okay, so let's see. 36 P3, that's going to be 42,840. 36 P4 is going to be 413,720. And 36 P5 is going to be 45,239,040. And with the drum roll, we get a grand total of 46,695,600 passwords that can be 3, 4, or 5 characters. And again, everybody says, well, why is there so many? There are so many because the order matters. Okay, so that's how many passwords we can get. Now let's look at the next one. It says, suppose that Jack's computer randomly sets his password using all the restrictions given above. We want to know what's the probability that his password contains only the letters of his name. Interesting. Well, I know the denominator is going to be what we just figured out. Okay, because that's how many total passwords we have. Now, what we need to figure out is how many passwords, okay, so how many passwords with the letters J, A, C, K. Okay, so how many letters do we have to choose from, guys? That would be 4, right? We said that the order matters. Now, of those 4 letters to choose from, we have to pick all 4 of them, right? The letters, the password has to contain the letters of his name. So that's why this is 4P4. So 4 letters to pick from, that's the first 4, and 4 that we have to take, okay, because the password has to contain all of them in his name. Okay, so this is going to be 4 factorial over 0 factorial, or 4 times 3 times 2 times 1, or 24. And so this is the probability. Okay, and the last example, we made it. We've got Tina. Tina's packing her suitcase to go on a weekend trip. She wants to pack 3 shirts, 2 pairs of pants, 2 pairs of shoes. She's got 9 shirts, 5 pairs of pants, and 4 pairs of shoes to choose from. How many ways can Tina pack her suitcase? We assume everything matches. Okay, well, good for her. All right, so in this case, what we have to consider then is how she's going to be packing things, right? So she wants to make sure to pack 3 shirts, 2 pairs of pants, and then there's a little word here. Everybody see that word? And, right? So she wants shirts and pants and shoes. Now in probability, what did you do when you had and? We multiplied. So I'm writing a little dot there. So I know I have to use the multiplication, okay? Now, does it matter the order in which she packs these things? And the answer to that question is no. Okay, so order does not matter. Doesn't matter. So this means combinations, okay? All right, so for the Shirts. How many shirts does she have? She's got 9 total shirts. Okay. And how many does she need to take? She needs to take 3 of them. We multiply. Okay. Next is what? Pants. She's got 5 total, and she's taking 2. And we multiply that by how many pairs of shoes? She's got 4 pairs of shoes, and she needs to take 2 of them. Okay. So you're going to run your formula and run the computation there, and let's see what we get. So 9C3, that should be 84. Punch that in your calculator. 5C2 is going to be 10, and 4C2 is going to be 6. Multiplying all that together, 5,040 ways that she can, she can pack her, circle that, and an eraser came up. So 5,040 ways she can pack her suitcase. So good news, guys. Tina's got her suitcase packed, and we're done with Chapter 4. So we move next into one section in Chapter 5, which is actually pretty cool application. So I'll see you on that side.